All right. Well, good morning, folks. Welcome back. A quick note about the exam yesterday. I know that a couple of periods had some issues that we had to work through. Actually, all the periods we had something to work through. But that's all right. That's to kind of be expected. There will always be a few glitches that we'll have to deal with when we're trying something new like this. And so, I think if we have to continue on with this format here, what we'll do then is that I think we'll work out those glitches for the next exam, and then I think it'll run a lot more smoothly for our classes. Okay. I've looked at the exam, what you submitted, and I think most of you were able to get the work done pretty well. So that's pretty good on a quick first analysis. What I do want to make sure I remind you folks of is that make sure with the written work that you have to do for the short answer questions, you have to make sure you submit that on time, folks. I know that since this is the first time, we're going to have issues, and so I've accepted all the work. But for the next exam, make sure then that you submit the written work by the time that the exam is over. If not, then on the next exam, I won't count it. Keep this in mind. This is an exam. It's if you're turning in the written work late, it's akin to, let's say, you taking the exam in class, doing the multiple choice in class, taking the written portion, the calculation part home, working on it, and then bringing it back the next day. Okay, so that we cannot do for the next exam. So this exam, that's fine. Like I said, this is the first one. It's to be expected. Make sure you understand then that if you do have issues with your downloading or the issues with your connection, then make sure you email me or let me know. And that way we'll work something out. But just please keep in mind for the next exam, all the work has to be in on time at the end of the testing period. Okay. Outside of that, I think I commend you folks for for being able to get that done, and I'm working through that. Okay. All right. So I'll try to have those scores back to you hopefully by the end of the week. We start our spring break, so tomorrow will be the last lecture before we leave for Easter vacation. So over Easter vacation, I won't be posting anything for you. Very much like in school, you'll have that time off. We'll meet again after Easter break. Where it'll depend on what we hear from school. Okay, but hopefully we'll be able to meet again back in school. But we'll wait and see. Okay. All right. So. Let's go ahead and do this. Let's start out the new material. Then we're going to continue with chapter 13 today. We'll continue to talk about the kinetic molecular theory. I'll introduce that to you. We'll talk about gases. Remember, our new unit here is going to be based upon gases. This discussion in chapter 13 will segue what we'll talk about in chapter 14 with gases. Our next exam, the material will cover chapter 13 and 14. We won't have a separate exam on chapter 13. Usually I combine these two chapters together, and so we'll do that. So your next exam will be on chapter 13 and 14. Okay. However, the material that you learned in the previous three chapters, you'll need to continue to remember, because in chapter 14, we get back to doing conversions. We'll do a couple of calculations, or we'll do one calculation in this chapter, but you have to make sure you remember that. Okay. So with that said, then, what I would like you to do is take a look at these three problems here, these three conversions. These are from, this conversion is from chapter 10. And so let's work on this here to start out the class period with, and we'll use this to review what we did back in chapter 10 and what you need to continue to know how to do as we move forward. Okay, so let's take about 2-3 minutes. I don't think this should be too difficult for you. Let's get this problem done, and then when we meet back after you get your answers in there, I'll work out these problems for you. Make sure you write those down, and then you'll submit this work at the end of the video. Okay, so take about 2 or 3 minutes. Let's work on these three calculations here. Okay. All right. Let's go ahead and let's take a look at these three conversions here. Let's work these out together. Okay, and let's keep in mind how we do this. Okay. All right, so these are three basic conversions that we talked about back in chapter 10. Okay, so starting out with the first one. Okay. Let me go and write this one. We have then potassium nitrate, and we were told that we have a mass of potassium nitrate of 47.8 grams of KNO3. Okay. And we were asked to find the mole equivalent of this particular compound here. So we're going to convert that into moles. And so this is a mass to moles conversion, which means that we need to use the molar mass here, the molar mass of potassium nitrate, which is 1 potassium, 1 nitrogen, 3 oxygen, which is going to be 101 grams. We're going to divide by the molar mass since we want the moles of the compound. Okay, and so we'll divide by 101 grams KNO3. You plug that in. Again, we do that. We divide here so that we can get we can eliminate the units of grams potassium nitrate, and then you'll get your answer then to three significant figures as 4.73 times 10 to the minus 1. Okay, and that's the first conversion. Okay, let's take a look at the second one. Okay. Here we were given volume. We're told that we have this volume 2.2 to 2.22 liters of sulfur dioxide of this particular gas. Okay. We want to convert that into moles of SO2. The conditions here have to be at STP for us to do this conversion, so make sure you keep that in mind. And if the conditions are at STP, and if we're dealing with the gas here, we can use the molar volume in order to do this conversion. The molar volume, remember, is going to be the same for any gas. The identity of the gas, okay, will not really matter. Okay. And so with that said, then we can divide by the molar volume, eliminate that unit, and we end up with our answer then as 9.91 times 10 to the minus 2. 10 to the minus 2 moles of sulfur dioxide gas. Okay. All right, let's take a look at the third conversion here. Here we have then particles. We're told that we have 2.25 times 10 to the 22nd particles of PCl3, phosphorus trichloride. We want to convert that into moles of phosphorus trichloride. So here then we will divide by Avogadro's number, because Avogadro's number is the relation gives us the relationship between moles of a compound or a substance, an element, I'm sorry, and the number of particles of that particular substance. And it's always going to be this number, PCl3. Okay, that cancels out that unit. You plug in your number then, and then you get, I'm sorry, down here for you, 3.74 times 10 to the minus 2 moles of phosphorus trichloride. Okay. All right. So with that said, all of these here should be the three significant figures. With the last one, kind of not really as important, but make sure you practice that as well. Okay, so if any part of these conversions here then you're not quite sure, please make sure you review that in chapter 10 or come by this afternoon from 1:30 to 2:30 to get that extra help with it. Okay. All right, let's continue on with where we left off on Wednesday of last week. We started this discussion of states of matter. And I told you then that in this chapter, we're going to examine all three states of matter, but I'm going to really emphasize the gases because this discussion of the gases in this chapter will help us then to move on to chapter 14. So let's go ahead and let's quickly remember what we talked about with gases. Then remember that it has properties that make it very different. So the state of matter that we refer to as gas has properties that make it very different both on the macroscopic level and microscopically from liquids and from solids. So with gases, then we talked about this and we used it to our advantage when we solved some problems. Gases then on the macroscopic level, we can observe that it takes the shape of its container and that it has the volume of its container. Now, that's if we see gas that we can see, for example, chlorine gas here, which gives us a greenish tint, we can see that the gas spread out. But the one property of gases that we can observe and we can measure for the most part is going to be pressure. It's very difficult for us to measure the volume of the gas. I mean, essentially, the gas takes the volume of the container, so we can just measure out the volume of the container, and that's the volume of the gas. But with that said, then the one property of gases that we can experience and we can see and we can measure for all gases is going to be pressure, and how that gas exerts the pressure we'll talk about in just a moment after we discuss this kinetic molecular theory. Okay, but these are the other properties of gases that we talk about on Wednesday. Okay, and so with that said, then the one key property of gases that's going to help us, and actually the key property of all particles in all states, okay, is that those particles are always going to be in motion. Okay, for gases, then the way that it moves is going to be very similar to how liquid particles move, and different from how solid particles move. So what you need to keep in mind then, as we move forward, we talk about this kinetic molecular theory of gases and of solids and of liquids, is that gas particles, and this is, and then when we discuss the kinetic molecular theory, we're talking about the description of motion at the molecular level, at the microscopic level. Okay? So at the microscopic level, at the atomic level, at the molecular level, particles are in constant motion. Movement is a constant in the universe, folks. And so when you study physics, and I think I mentioned this already, when you study physics, the very first semester in physics is studying motion. Motion is a critical part of everything that happens in the universe, and we can almost describe almost every phenomenon based on motion. Okay, so with that said, then when we apply what's called the kinetic molecular theory, which in its simplest form just basically stipulates in that everything is in constant motion at the molecular, at the atomic level. Okay, and so with that said, then there's as an object moves, there will be energy associated with that motion. Now that's going to be important, and we'll talk about that in just a moment with the next slide. But energy and motion are going to be related to each other. When we start talking about temperature, hopefully tomorrow, if not after spring break, when we talk about temperature, temperature is heat energy, and that heat energy is going to be directly correlated to the movement of a particle. Okay, so heat energy and what we call our kinetic energy are directly related. Okay, so we'll talk about that as well. And so what you want to keep in mind then, we're going to be referring to, we will be talking about this heat energy here, or kinetic energy, which is the energy of motion. Okay? And so the kinetic molecular theory basically says then that any object, when it's in motion, will have a certain amount of energy. Okay, and that matter and that all particles are in constant motion, and that's what you want to make sure you keep in mind. Okay, all right. Okay, so because they are in constant motion, okay, there'll be certain properties of these gas particles that we can examine. Specifically, then we can examine then, for example, the pressure that the gas exerts and its relationship to temperature and volume as well. But do keep in mind that as you move forward, because these particles are always moving, and the nature of their motion is what we describe then as random, rapid, and constant. They are in constant motion, these gas particles, and that's the basis of the kinetic molecular theory. And we'll apply that also to liquids and solids. But these gas particles, they constantly move, and the way that they move is going to be very fast. They're going to move very fast, even at the fairly low temperatures. They will be moving very fast, and that their motion is random. That means then that they don't move in a straight line. They're moving in all sorts of manners, and that random motion has been given a name. We sometimes refer to it as Brownian motion, which was also applied to biology. And you can imagine that if you look at a dust particle, when it moves, if you've ever sat and you looked at the dust move, you'll see that those dust particles move in a random way. And the reason why the gas particles and we have this random motion is just the gas particles are always colliding. They are always bumping into everything around them, and that's what you want to make sure you keep in mind. Okay, the gas particles, this collision here, they're always bumping around, colliding with each other. And because of those collisions, and these collisions will define then as being elastic, what we call perfectly elastic, because they are constantly bumping into everything around them, they will exert what we refer to as a pressure around them. And it's that movement and the collisions that creates the pressure that we feel. And we do feel these gases that we feel and we can measure as the gas pressure. Okay? All right. So let's go ahead and delve into a little bit more of this kinetic molecular theory. In physics, we just define this energy of motion. Remember I told you that if any object is moving, it has a certain energy associated with it. That energy then is what we refer to as the kinetic energy. Kinetic meaning then that movement. That kinetic energy can be calculated. We can calculate for that kinetic energy if we know using this formula here. Okay? So this formula here gives us then the relationship between kinetic energy and the mass of an object and its velocity. V here stands for velocity, which simply means how fast something is moving. Velocity is the speed of an object with the direction taken into account. That you really don't need to know. You'll learn more about that if you move on to take physics here. But do understand this, what this equation is telling us is then that there is a direct relationship between mass and kinetic energy, meaning the larger the object is, the more kinetic energy it will have. Okay? But it also tells us that this kinetic energy here is related to velocity and the square of the velocity, meaning then the faster an object moves, the greater the kinetic energy that it will have. So the larger the object, it'll have greater kinetic energy. Okay? And the faster the object is moving, it will have greater kinetic energy as well. Okay? And so hopefully you see there then, for anything to have kinetic energy, it must have a mass and it must be moving. Because you can imagine here, if the velocity is 0, meaning that the object does not move, it will not have any kinetic energy. And you got to keep this equation in mind. I won't ask you to do any calculations using this equation here, but what you want to make sure you understand is that you need to remember the relationships that I just pointed out to you here, and that is the relationship between the movement of an object and its energy. Because everything in the universe has mass. Okay? Everything in the universe has mass. But because not everything in the universe on a macroscopic level is moving, not everything on the macroscopic level has this kinetic energy. However, on a microscopic level, and this is where the kinetic molecular theory, this is one of the central tenets of this theory, and that is on a microscopic level, at the atomic, at the molecular level, everything is in motion. And because everything is in motion, everything at that level has this kinetic energy. So make sure you keep that in mind. Okay? And because of this, we refer all gas particles will have this kinetic energy. And like I said, hopefully tomorrow, if not tomorrow, after spring break, the fact that these gas particles are in constant motion is going to be directly related to the amount of heat energy that it experiences in its environment. Okay. Okay. All right. So let's go ahead then, and let's continue on and talk about this this random rapid motion. So with kinetic molecular theory, again, it stipulates that everything is in motion, that the gas particles themselves move in a random, rapid, and constant manner. And make sure you keep this in mind then, that as we go forward and we get to chapter 14, these gas particles then are very, very small. Okay? They're very, very small. They practically have no volume of their own, and they have no interactions between the gas particles. Okay? So those are other stipulations that they make when we go forward with this kinetic molecular theory. Okay? Well, let's talk about this random walk really quickly. Okay? And again, the reason why the gas particles move in this random manner is because they collide. They collide with other gas particles around them. Okay? They collide with everything else around them, whether it's the gas particles or the walls of a container. They are in constant collision. Okay? Because if we know that they would be in constant collision, because let's just take a simple example to illustrate this point. Okay? So if you think about this, if a gas particle moved and it did not move in a random manner, that it just moved in a straight line, you can imagine then what would happen. So for example, if someone were eating a pizza, we can smell the pizza because we are sitting in the room fairly close to the person, and we have to be fairly close to the person to be able to smell the pizza that he or she is eating. However, if a gas particle moves, and I'll get back to why that isn't just the case, in just a moment. But let's examine the case then if the gas particles move in a straight line at roughly room temperature. At roughly room temperature, and I'll finish up with this here, folks. The gas particles move at a speed roughly about 1,700 kilometers per hour. That's how fast a gas particle will move, in this example, than oxygen, at little less than room temperature. If this were the case, then if you were eating the pizza in Washington, D.C., for example, someone would be able to smell that pizza in Mexico City in little under an hour. Okay. Now we know that that's not true. We know that that's not true, and the reason why that's the case is we talk about the dilution of the gas particles, the odor that the cheese pizza gives off, but the reason why it gets the smell, the odor, the aroma of the pizza stays fairly localized, and you'd have to be fairly close to the person eating the pizza to smell it, is because these gas particles are always bouncing off each other. Okay, and so the air that we breathe has a lot of gas particles in it, and so as the aroma the cheese spreads out, it's going to bump into these gas particles around it, and because of that, the gas particles that emanate this aroma that emanates from the pizza stays localized. Now, a few of those particles do get out, okay, and then so that's why we call it it dilutes in the air. Okay, it gets out, and as it mixes in with the air, it dilutes. So that also prevents a person in Mexico City from smelling the pizza that a person eats in Washington, D.C. Okay, okay. So with that said, then what we're going to do is we'll talk about this. So understand then that these gas particles they undergo these collisions, and these collisions then keep the gas particles fairly localized. But it's those collisions that will account for that. The pressure that we're going to talk about, and I'll finish up with this here. The pressure that we feel and the pressure that we experience from the gases. And these gases do exert a pressure on us. And so when we talk about atmospheric pressure tomorrow, you'll see then that atmospheric pressure is the gas particles in the air affecting us and interacting with us. But because those gas particles collide, okay, the nature of their collision is what we refer to as elastic collisions. And you can imagine an elastic collision being basically the two gas particles colliding, they hit each other, and they bounce off each other. Okay? Now, the difference between the collision, the elastic collisions that they experience, and I think on a macroscopic level, on our level, what you can imagine then is, let's say, a bouncing ball. Okay, a bouncing ball kind of models what we refer to as these perfectly elastic collisions. But the key difference here is this: that with perfectly elastic collisions, the energy that the particles have before and after, the energy that they have before and after the collision remains exactly the same. The overall energy of the system remains exactly the same. Okay, so you can imagine this: if the bouncing ball did experience a perfectly elastic collision, when you drop that ball, okay, it would bounce right back up into your hand. Now we know that's not true, because what the bouncing ball does is it loses energy as it collides with the ground, and that doesn't happen with gas particles. Gas particles at the level of the molecule and the atom, when they bounce off one another, the energy that the system started out with remains exactly the same afterwards. And since gas particles are moving very fast, okay, they have a large amount of kinetic energy, and so the overall kinetic energy is not going to be lost. Okay, the gas particles in themselves also maintain fairly constant kinetic energy, and that's what leads to the gas pressure, okay, that they exert. Okay, and so what we'll do then is tomorrow we're going to talk about then this pressure, and this is the example here, folks, of how we can experience gas pressure. Because you can imagine this: when you blow air or when you put gas into a balloon, what is it that keeps this balloon inflated? Okay, and so we'll answer this question tomorrow, and from the answer to this question, we're going to see then that the gases all do exert this pressure, and that's how we know that gases are there. Okay. All right. So with that said, then for tomorrow, then we'll continue with this discussion of gas pressure. It's going to be a little bit heavy on the physics side of things, and so please look ahead in your book. I will not assign any problem for you to do after here. So basically, just turn in the one conversion problem that we did at the beginning of lecture today and submit that for today's work. Okay. All right, folks. So I will see you folks tomorrow, and we'll continue this discussion of gas pressure.